down to sure. Wonderful.
We're live. And the speaker is Ben Steer.
Wonderful. Good afternoon, everyone. I am Ben Steer. I am the CTO of Pometry, and I'm here to talk about our temporal graph analytics platform, Raphtory. Now, before I start, I just wanted to give a bit of a background on the whole Pometry ecosystem. So I previously, before Pometry, was doing my PhD at Queen Mary, where I was looking at temporal graph analytics. So these are networks that evolve and change in time. And as part of that, I built this platform called Raphtory, which would allow people to sort of take their data from any data source, convert this into a network, and then see how that network has changed, embed time into the queries that they're running, and so on. My co-founder, Al Hamza, who you'll see kicking about at the conference if you're here in person, was in parallel working at a company called Quantexa. So this was an anti-money laundering, anti-fraud company. And a lot of the tools that he was using were sort of woefully inept at being able to process networks and time together. So we were chatting about this for a long time. And on the basis of it, we founded Pometry, develop an enterprise version of Raphtory that could scale to the size of data that he was looking at. So in parallel with that, Raphtory is actually funded as an open source project. You can go and give it a try now if you like. And there's loads of contributors from a variety of different universities that are working on interesting temporal problems that we'll get into. So in this session, I'm going to go over what's interesting about the temporal graph model, what it is and why you should care. Explain why temporal graphs are pretty hard to process, and if you're trying to do this on an existing solution, it's probably doomed to failure. And how Raphtory sort of addresses these challenges, how it works, and then actually, interestingly, in a lot of traditional graph use cases, you can really reduce your runtime down a lot. So let's start with the temporal graph model. So when we talk about temporal graphs, what I like to imagine is that when you're going from static data that's sort of, the most recent version of your data all aggregated at one point, you kind of lose the underlying story. You don't get this evolution of what's happened. So we can kind of compare this to a real story. In this case, let's have a look at Lord of the Rings. At the start of this, you have Gandalf, he's kicking it about in the Shire, he's chatting to the hobbits, and then later on, he runs off and he's off on his adventures with Legolas and Aragorn. So if we were to view all of the interactions in Lord of the Rings right at the end of the book at one point in time, it's very difficult to see this story. You don't get this, you just see these interactions, there's no sort of arc here. What some people may do as a sort of solution to this is you take snapshots. Okay, I'm going to look every day, I'm going to look every month. But this is very coarse. You don't really see what's going on in between these points in time. And if you want to have a look at, how, say, communities are evolving or decaying, it's very, very difficult to do that from explicit snapshots. What I suggest you do instead is that actually you build up a full historical log, and you can see, every individual time point, how the network has changed, how these interactions are evolving. And then ultimately you want to be able to bake this into your queries and ask questions around it. And that's ultimately what we're trying to get through with a temporal network, temporal graph. So Raphtory's temporal graph model, it can be viewed in the premise of a stream. So we have events, the adding of nodes, the adding of edges, editing properties on the nodes, so that you can have a full historical log of the properties, and then also deletions. So you want to be able to store the absence of information. This edge didn't exist for this period of time. And then if we swap this into an actual network built from this data, we can say we have Gandalf and Bilbo. They were friends at the start. They had a little argument in the middle, so this time at T5, and then they become friends again. So you can see, that you have these this absence of information in the middle, and then obviously this change in properties. Gandalf used to be a grey wizard, now he's a white wizard. But if we go back in time, we can see exactly what it looked like at that point. Right, that's all good and wonderful. Why should you care? So we'll go through a couple of individual use cases. One that's a bit more abstract, one that's a bit that's sort of concrete that we've actually worked on in the past. The first of these is then having a look at different patterns through time. So these temporal motifs in networks, through the premise of, in this case, predicting defaulting behavior for a bank. So if we have, say, a set of merchants, these tend to have income dependent on multiple buyers, so people purchasing their goods. So we need a way of capturing this model of money for goods as a set of relationships in time, which I would say is a temporal network. We have people making transactions, these occur at set points, and you can infer information from this. So let's say we have a bank that gives a loan to a merchant, and maybe a car seller. People purchase these cars off of this car seller, and then the merchant's able to pay back their loan. And we may see this sort of temporal motif multiple times over a very large network of transactions. Well, if we have, let's say, a bank giving this loan, but then no one's purchasing any cars, well, it's pretty fair to say that there's a big risk that this merchant's not going to be able to pay back their loan. So we may be able to contact the merchant, get ahead of this problem before they default. And these sort of patterns are directly translatable to a lot of different use cases. For example, if you have DDoS attacks in a network, you can get ahead of this very quickly. We do a lot of semi-supervised learning for labeling in crypto networks, so you can find mixers, different automated services by the updates to their software. So there's a variety of different things that once you include time into these patterns, you get a lot more out. So as this is knowledge graph conference and more ontology based, I wanted to pick a use case that was a bit more sort of factual in terms of actual documents. So we worked with a company called Mishcon de Reya. It's a legal firm. They had 400 years of legal judgments. So this is when you basically have a court or a lawyer will say something for a case, and then later on someone else will cite these papers as a way of saying, like this backs up what I'm currently saying now, to sort of say the other guy's argument is poor or my argument is good, etc. And this happens periodically throughout time, and you get very important documents that are the basis for all of legality in the country. What they were interested in is if you have over the whole world lots of different jurisdictions, all of which have their own laws, all of which have their own corpuses of documentation, how are these different places citing each other, and then the different sort of legal systems affecting each other around the world across this whole period of time. So this, going, I think actually Magna Carta was in this data, so that may be slightly wrong, goes all the way back to like the 10th century or something ridiculous. So we run a variety of different algorithms on here because they wanted to have a look at could they predict sort of sleeping giants, documents that are not very well cited now but are going to be in the future. Picking one of these algorithms out of the hat, we can have a look at something like connected components, which for people that have not seen this algorithm before, the general gist is that if you have nodes that are reachable from each other, they're in the same component or community. So for example, here we have community 1 or component 1. All of these nodes have a path to each other, and there's no path to any of the other nodes in the other communities. The largest connected component is then the sort of largest community in that network. And the reason this is interesting is that, if everyone's densely connected, this is very, very interesting comparison to maybe some little communities out on the periphery. So what we wanted to do is run this analysis through time, so find the largest connected component in comparison to other sizes, but not just look at the aggregate network, so your kind of snapshotting view of things, where you're just, incrementing the data as it goes along, but look back different periods of time. So for each year, look back a year, 5 years, 10 years, 25 years, etc., and see how the network varies. So for example, the general aggregate network shows that the largest connected component or largest community just continues to grow. But actually, if we look back 5 years from each year, we can see that around the 1960s, you had all of the national independence from the British colonies, and they started out their own corpuses. They stopped referring to British legal documents. Alternatively, if you look down to the individual year window, you can actually see the rise of the internet. So in the 40s and 50s, very few communities, legal communities, were referring to each other's documents quickly. But actually, as soon as things become digitized, become online and available, all of the different communities sort of merge together. So what can we kind of learn from this as an interesting point? Well, if we're only looking at aggregate data, as most people may do, you can just say, okay, well, our community is growing continuously. But if we look down in a 5-year window, we can say world events are drastically affecting the structure. And even lower, we can extract out individual things like the growth of the internet. And without including time in this sort of analysis, we would have missed out on these important insights. So hopefully that's convinced you somewhat that there's some interesting use cases around temporal networks. So why is it hard and why is no one doing it? Well, the first thing is that because there's no real specific solutions for this, code can really get messy quickly. So if we have a look at an example, like I want to get the weekly PageRank scores in my social network from the start of the data set to the end. So I tried to push this together in as many data scientists may do inside of pandas or inside of Python. And what this generally looks like is I build a data set out, I specify a time range, so in this case a week and a specific range. I'm then going to loop round this data, filtering it out, and building out my network and running the algorithm. Now, I'm not the best programmer in the world, but I'm certainly not the worst. But I needed to fix an awful lot of pandas errors to get this to work. And then when we start to get into, if I want to aggregate monthly instead, annually or all time, or, I want to add some additional filtering, this becomes very untenable. And then if I come back a month later, I forget, how all of this works all together. The other aspect here is that once the code's actually working, good luck running it on your full data set, because we're making several passes over the data, one for each time point, one for each window. And then we're reconstructing and discarding all of these graph objects. This does not scale for large data sets over long periods of time. So for example, the citation graph that we had 60,000 different views of the data. This is not something you want to continuously load and discard from your database. Secondly, if we're looking back at our like defaulting behavior algorithm, this is one temporal motif, or in this case, a triadic motif. Even if you don't look at things like ranges in time, there's an awful lot of ordering we can think about. And then, if we have more nodes involved, more interactions involved, this goes massive. So there's two problems here. One is obviously it's computationally hard. And then there's also a question of how do you even represent these queries in time? How do you specify I want to always hop forward from the time that I arrived at a node? Lastly, we've talked about data that's like a stream of events. Well, what if I only got network snapshots? So I only got information once a day. Or alternatively, what if my nodes and edges had some duration? So I specify when they're created, when they're deleted, and when they're created again. For all of these, if you've built some code like I just shown, you would need to rejig your model, rewrite this code, etc., because the existing tools really aren't designed for temporal networks, and Raphtory is. So what is Raphtory and how does it work? Raphtory is basically a set of decentralized distributed services which together will build up a temporal network and allow you to compute different algorithms on it. The first sort of block of components we like to split is called the ingestion and modeling set, which starts off with a spout. The spout is kind of the insertion point into Raphtory from the outside world and allows you to pull in data from things like CSVs, Hadoop databases, different streaming services, etc., and extract out individual tuples. Those tuples are passed into what we call a graph builder, which will, via user-defined functions, convert that into a set of graph updates. So this is your adding edges, adding nodes, removing edges and nodes, and updating their properties. And that's all you need to do as a user. After that, this is pushed off into a set of partitions. These synchronize amongst themselves, expose the full history and the graph structure to the user for querying. On the other side, your data scientists, your business analysts can then submit queries which will contact the partitions, complete the analysis, and return the result to you. So if we look at how we'd actually create our own temporal graph as an individual example, we may have some CSV data that's on disk. This could be, say, for a social network. We can split this up via, say, a friendship builder, which will then build a full network of, let's say, me and my friends over a set of partitions. It may be that once we've ingested all of those CSV data, we then want to attach a Twitter fire hose or some stream of information, which will continuously update it through this same friendship builder. Or alternatively, we may take these two spouts, these two pieces of data, and then push them through a different builder instead. So in this case, instead of taking out the friendships, we're going to extract conversations and then build up these different trees of tweets and replies. So the premise here is it should be as easy as possible for you to go from your raw data into a graph model and have this fully distributed. Once you have your kind of idea of how you're going to build up your network, one of the aspects that we've seen in a lot of graph platforms is that it's sometimes a bit of a nightmare to deploy their sort of sealed units. So for Raphtory and specifically the Pometry version of Raphtory, everything is automated via Kubernetes, Terraform, and Helm. So you can push these up on bare metal, you can push them up in cloud, etc., wherever it is you like. We can pull from data storage and different big data tools and push back to those. So this really the idea is you can clip this into your pipeline wherever you like. You can pull from your data store, push this into Spark afterwards, or pull from a running Spark job and then push this off down your downstream. Or alternatively, there may be some mid-tier services, things like alerting, visualization, discovery, etc., that you want to push your results into. Right, so you've got your graph modeled, you've got your system running. What sort of algorithms can we run on top? So this may be old hat for some people. This may be a new idea for others. In Raphtory, instead of thinking like a graph, which is your sort of queries, thinking about the network as a whole, we do what's called thinking like a vertex. And the premise with thinking like a vertex is that for an individual node, it can see its own state, its own properties, its own history, and that of its incoming and outgoing edges. So these nodes have no information on each other. And then you'll propagate messages throughout the network to your neighbors so that you can generate some final global state. And the wonderful thing here is because the vertex is this kind of atomic unit of processing, you can distribute them as much as you like across any number of machines, and your algorithm will run exactly the same as if it was on one box. We have a free tier API for our vertices, which at a base level is this kind of vertex state querying. So this is asking questions on the vertex itself, its history and its properties. We have an algorithmic structural layer on top of that, which allows you to define how your algorithm flows. So how you step through, you iterate to convergence, filtering, selecting out the results you're interested in, etc. And then a sort of secondary temporal layer, which is once your algorithm is defined, you can then run this at any point throughout the whole history of your network. So it's kind of define an algorithm once, run it forever. So if we look back at the previous example when I was talking about the citation network, we defined the connected components algorithm once and then run it 60,000 times over different points. And Raphtory deals with the generation of all the perspectives and different views of the graph underneath. Out of box, there's a variety of different algorithms that are already available. So there's sort of generic ones that you'd expect like PageRank, but also kind of interesting ones like Temporal LPA, where you have this sort of vector of all of the communities that you're in across time and can decide whether you are interested in the structure now or your structure in the past and future. But once you get your head around this think like a vertex idea, it's very, very easy to define your own algorithms. And the reason being is because they basically follow a very simple structure of gather information from my neighbors, calculate some state about myself, and then propagate that out. So for example, we may have here a node which gets some information from its neighbors that says, hey, most of my neighbors actually have the lilac label, so maybe I should be lilac too. And then in the next step, it will propagate this out to its neighbors. This will continue on until everyone has the label that they think is correct. And then this result can be returned to the user. So this is great for things like PageRank, connected components, community detection, etc. And all of them kind of fall into this same structure. So there's probably a couple of you who think, oh, well, I've seen loads of iterative algorithms before. What's kind of fancy and new about this? Well, the great thing is you can actually bake time into these queries as well. So when we're doing our propagation, we can do this on interactions after or before when things occur. So for example, let's say this node in the middle has become infected with COVID-19. He's found out this morning. And he says, okay, well, I'm going to message my neighbors and find out who was infected yesterday. He says, oh, well, this guy, when I bumped into him on Tuesday, he was the one that was infected. So now anyone that has an interaction after this, they're the only people that I'm going to propagate this down. So these other two edges on Monday and Tuesday at 4 p.m., we don't propagate to those guys because there's no way I could have infected them. And the really interesting thing here is that when you're following these time-respecting paths, you actually massively shrink down the search space that you're pushing forward and you're propagating in. And it means that you can go many, many, many hops deep in comparison to other systems, which we'll come on to in a second. So we now have our algorithms. What do we do with them? Well, as I was saying a minute ago, we have this idea of graph perspectives. So this is looking at the network at some specific point in time. So we can have any network, let's say 2 people making transactions, and we have a timeline. So we may want to run a point query. So this is saying, I want to have a look at what the graph looked like at this exact point in time and run this algorithm. I may want to specify ranges. So I'm going to move every day throughout a year running this algorithm and return the result for all points. We can specify windows, as we saw in the original examples, looking back a period of time, or batches of windows. So I want to look back an hour, a day, a week, a month, a year, all in parallel, and get the results back for all of these to compare short and long-term patterns. And then, of course, because it's a streaming platform, you can also run live queries on the most recent version of the data. And there's an absolute final point. Raphtory is designed to run at scale. So to give you a little bit of an idea of the scale that we're looking for and the sort of speed that we can run at the moment, a couple of people that we're working with in the crypto space have been tracking sort of illicit services across the blockchain. So the general premise here is that we want to find time-respecting paths following bad money. So this is someone has stolen some money from an exchange, and they're now trying to propagate that throughout the network, hundreds and hundreds of hops deep, to hide it and get to an exchange where they can turn it into fiat, and run off to some island somewhere where they won't be extradited. So we want to work out here, who's pocketing this money and who are the accomplices. So as a kind of benchmark for this, we ingested in the full Bitcoin blockchain, which on one machine took 49 minutes for the full 600 gig of data to be ingested. And then once it was in our internal format, it takes 1 minute to re-ingest. So you can spin the box back up. And really the only limiting factor here is disk speed, which I think is very, very exciting. Doing the analysis on this, so doing this time-respecting diffusion on the full network, we started with 30 million nodes in parallel as sort of initial bad actors. And the only stop conditions is that we reach the most recent point in time. So, the money has not been exchanged yet, or we have a stop condition like we hit an exchange. So you can go and tell the police, hey, this bad guy has, tried to exchange his money at Coinbase, go and give them a bell and see what's going on there. So this actually produced full paths up to 691 hops deep. And it only took around 400 seconds to converge. So I think this is super exciting because most of the time, a lot of these bad guys, they go hundreds and hundreds of hops deep. And most systems will just kind of give up and say, okay, these wallets are fine. but hopefully now they can run, but they cannot hide. So in summary, graph analysis is already really, really hard. And if we try to do this 100,000 times over on different versions of your data, it becomes intractable. We like to think that Raphtory is the solution to this. We can deploy on anything. We can ingest from anywhere. They're really reducing data silos down here, and it's super easy to use. And just some juicy metrics again. There's 3.5 billion records loaded in 47 seconds for Bitcoin. And if you run that from that tainting from the very start of time, we can actually go 32,000 hops deep, which is a bit absurd. Why you should care. We think we're transforming graph analysis to seamlessly embed time in your graph queries and finally understand the sort of real story underlying your data. That I say, thank you very, very much for listening. If you're interested in joining the conversation, learning more about Raphtory, come join our Slack. If you want to give it a try, it's available on GitHub. And if you want to get it into your tech stack, give us a bell. Contact us on Pometry.com. If there's any questions, thank you.
All right, thank you. Let me ask a can you say anything about bitemporal representation?
Yes, you're not the first person that said about this week. So we're very interested in this kind of as is, as was sort of relationships of, I guess, multiple timelines. In the way that we've been dealing with this at the moment is kind of on properties on the nodes. So you can specify like, I knew about this fact, I had an estimate of this fact at this point in time and have a sort of a history for that. And then the sort of solid facts of like, I knew this at this time as a separate property, and then compare those in your algorithms. So the wonderful thing about our model is because everything is chronologically sorted, you can insert like out of order information into the model and then rerun your algorithm. So it may be, you have one graph that's in memory, and then I have a load of new facts that I've learned, and they get pushed in, they go into the correct points in time, and then I can start having a look at, how things have changed with this new information that I've learned.
This is very interesting work, because in the world everything is time and space. These days with the internet and the speed, space becomes less important in many applications, because what I'm doing here right now can be copied in India, a second later. But time is extremely important. And as I had the exact same question as Ora had about bitemporal, we actually did a work with University of Leipzig in Germany.
Is that with Leonard
Roast.
Oh, okay.
Yeah, his group actually. So we we came up with. He did most of the work. He's a PhD student, so he does the work. We just sit. So he came up with this. They call it TPGQL, like temporal PGQL, right? Which basically makes it easier to specify some of the temporal constraints in the language, right? And the idea was that the property graph will actually handle. We used the property graph because RDF doesn't, as such, have the edge property easily, right, today. So he asked me actually which one to use. I said, go for property graph because it has today the edge property aspect. And so we are storing the bitemporal thing, right, the application time and the transaction time in there. And the query language that he proposed, which is an extension of PGQL property, right, that has that ability to specify those constants easily. So that's from a lower level point of view, right? And it makes it very easy that way, that's something like that, to specify such queries. Now, it's very interesting that you have this analysis, ability to analyze, because that with that information, taking into account that information, and the fact that you said that it takes only 423 seconds for doing such analysis, which would take a lot more for other things, is that because you are not repeatedly looking at going back and making getting that information again and again? Is that one of the?
I guess there's there's definitely an aspect here of there's an awful lot of people in, I guess, the graph database space that are doing wonderful work. We wanted to kind of focus purely on the analytics side of things, which is kind of why I'm talking about things like connect components and this kind of large scale tainting and so on. One of the biggest optimizations here really is that kind of time respecting element of where you're only propagating forward into. So the query is let's say I send some money to you on Monday, you send some money to Hamza on Tuesday, and then Hamza sends some money back to me on Wednesday. Well, when I'm hopping forward through the network, I arrive at you. I say I arrive, on Monday. I can only propagate from Monday onwards, and so specifying those sort of things, and actually the underlying implementation being based around it, actually seems to run. Yeah, it shrinks down massively what you're looking at. So that's definitely one of the larger optimizations. There's a lot of other wonderful stuff that's going on behind the scenes, but yeah, I think that's definitely one of the largest elements here.
Because didn't try to apply it to analytics. We went for the query language, and that was good work. But analytics is very interesting.
Yeah, I think on that as well, we've kind of got our own sort of language for doing these algorithms, because it's a super green space. Like, there's very little work on how do you actually talk about time when it comes to data. So I'd be really interested to speak to you afterwards, just to see if these two things can be kind of merged together in some way.
I have actually published a paper.
Oh, wonderful.
Okay. So if you want, I can send you the link.
That'd be fantastic.
Hi, I'm from Expedia. So in the travel space, the notion of when and where is important. And what you presented, it seemed that time is linear. Do you have any ways to represent seasonalities, recurring events, or things that are happening not in a linear fashion, but in a recurrence fashion, like summer, winter, and autumn seasons, or things like that?
So, when you're sort of submitting your query, I mean, I didn't show any kind of the code here, just to kind of keep it high level. But yeah, you can specify different sort of periods of time that can, they can be, you could say 3 months, or like, we could specify things like seasons. I mean, so something like that is maybe a little bit more niche than what we've got in the current API, but like this would be, adding an extra function. It sort of takes 10 minutes to kind of get that done. So yeah, all of these sort of specific specifications you'd have on time, you could build into your query. So yeah, the premise is that, once you've defined a couple of algorithms, you can run those really on any parameters. So I like to kind of think of it as like a right-hand and a left-hand filter if you have a timeline. So, I'm specifying a single point that I'm looking at. I can then look back or forward from that point, or in the middle. So I have like a smoothing effect. And then this kind of like increment of like how I'm moving through. So it may be that you're specifying per year, I'm interested in, these dates, which could be, like the start of spring, the start of summer, etc. And then looking back and forward from that point in time to see how things change. It would depend on the use case we're looking at, but yeah, it's definitely possible.
All right, anyone else?
Have you thought of any other dimensions besides time, like geospatial, like?
Yeah, so we actually have a really interesting use case. We were working with an insurance company looking at boats. And so we built a bipartite network of locations and boats, where the sort of connection was, the boat was in this position at this time, where the premise there was we were looking at the different sort of patterns or sort of trails that boats would take. And if we could find people that were doing ship-to-ship transactions, so there would be a boat from America that was going over to the Indian Ocean, meeting a boat from, say, China or something. They were trading goods at sea. That Chinese boat was then taking those goods to Iran. And so the American company was effectively breaking sanctions, but on paper, they were selling their goods in Dubai or something. So yeah, there's definitely different ways that we can bake that into the model. And that's kind of the point of the graph builder side of things, is that as much as the algorithms are interesting, one of the really interesting aspects is that you've got some raw data, which, let's say in a table, how do we, there's 100 different graph models we can build out of that. So yeah, no, definitely we've had some work in the geospatial geospatial temporal world. Yeah, very much so. It's a bit of a wacky space. Oh, okay.
We'll take one more.
Right. So actually, we're also working in the insurance space, so that last step was pretty interesting for us. I was wondering two separate things. First, what kind of expectations does your system have on the actual metadata or the way that things are tracked in our graph, as in RDF versus OPG, or like specifics around like how specific values are tracked? That's one set of the question. And the other, what if there's multiple timelines, as in there's a timeline when something happened, and there's also a timeline of when you learned that this thing happened, which maybe are used for different kind of purposes.
Yeah, so I think on the first point of like what it has to be, the only restriction on data going into Raphtory is that it has a timestamp, because if you don't have time, it's hard to do time analysis. So that's about it, really. On the secondary question, we're sort of dipping our toe into the bitemporal world now. My general feeling is that you can definitely represent both of these at the moment in the current model as different properties on the node. So, knowing what a fact assumption was or when you found out about a fact specifically. There seems to be so much interest in it. There's definitely something we're going to be building new APIs on top of so that you could, really get to this nicely. But I'd love to dig into your use case as well so that we get sort of a concrete idea of how this should work. Wonderful. Thank you very, very much.
And our next speaker is Jan Osman.
Yeah, I think the rest. Can't see the other one downstairs.